Good evening to all. I welcome you all for the third day faculty development program on titled Advanced Biomaterials for Orthopedic and Tissue Engineering Applications. Today we have the eminent personality uh, by name Dr. Mamilla Ravi sir, Professor and Head Department of Mechanical Engineering, IIT Tirupati. Sir listed among world top 2% scientists, and he's also listed in the top 75 with respect to inventive top Indian scientists. Sir is also acts as associate editor for Journal of Manufacturing, which is in quarter one journal with the 6.1 impact factor elsewhere. Sir as also a principal investigator and had received to a tune of 10 crore rupees of funding. He served nearly 7 years as assistant professor in Department of Mechanical Engineering at IIT Guwahati. Before he joins in IIT Tirupati, he did his BTech from Sri Venkateswara University, Tirupati, and MTech as well as PhD from IIT Kanpur. His research group focuses on nano finishing, micro nano manufacturing, sustainable manufacturing, precision 3D printing, online monitoring, biomanufacturing, coatings, tribology, and rheology. His lab also involves in development of lab scale innovations to commercial manufacturing products. He has published over 80 in internationally reputed journals, 150 international conferences, 10 patents, 5 edited books, and 15 book chapters. The knowledge transfer of his patents is already transferred to India's leading research laboratories such as CMTI, Bangalore. Presently, his lab possesses with various funding from BARC, DST, DRDO, MITI, Imprint, Verac, IGSTC, SERB, CSIR, IKS, CARE, ISRF of about 6 crore rupees as principal investigator and 160 crore rupees as a co-investigator. He guided 7 PhD, 52 MTech and 40 BTech students, currently guiding 7 MS and 20 PhD students. He is also the editorial member of IMECI Journal of Micro Manufacturing and guest editor for International Journal of Precision Technology. He is a recipient of prestigious awards such as Institution of Engineers India Young Engineers Award 2015 in Production Engineering, Indian Society for Advancement in Materials and Process Engineering, and the finalist of Indian National Academy of Engineering INAE Young Engineer Award for 2014. He and his students received 14 best papers and 3 best poster awards in national and international conferences, India and abroad. Apart from academic awards, he has also received Institute Blues, that is for Outstanding Sports Personality of IIT Kanpur for the year 2009 for his outstanding games and sports achievements. With this a very brief, very enlightenment biodata of Dr. Mamilla Ravishankar sir, I would like to hand over the platform to you, sir.
Yeah. Hmm. Thank you. Am I audible? Am I
Yes, sir.
audible,
Audible,
please?
audible, sir.
Thank you. Can you able to see my screen?
Yes, sir.
Yes, sir.
Yeah. I don't know why it is not going to full screen. Yeah. So thank you, one and all, who are attending. So thank you to Annamacharya. Normally, I love to deliver to any of the institute, uh, especially that comes in my district basically. So when I was a student at IIT Kanpur, Always my professor used to think that I have not done much work for Madhya Pradesh because he was belongs to Madhya Pradesh. So now he's serving to Madhya Pradesh because after retirement he went back to Madhya Pradesh. So looking at my supervisor, so I always think that when I was at IIT Guwahati and at IIT Kanpur, I was thinking what I have to do for my state. Then I came to my state. So I am already doing to my state. So it's always a privilege to deliver to my home district because I belongs to Kadapa district. So anyhow, Annamaya district and Kadapa district both are part and parcel of Kadapa district once upon a time. Whether some people may accept, some people may not accept. Anyhow, that is part and parcel of our blood. So United Kadapa district. So I am going to deliver on one of the things that I think there is some disturbance, so organizers can take care. So I'm going to talk about what we do, basically what I do, what it's also one of the works that we collaborate with my wife because she's anatomy professor. So what we try to do anatomically and most of the things. Okay, so nevertheless, I'm just going to talk on mostly on bioprinting that we try to do, and currently we have one that is called Luminex Plus, which we have got recently project, and I may say it was a 1.5 year project, and we have closed the project now. So bioprinting of in vitro mimicking 3D microfluidic channels for checking the efficiency of Ayurveda. So this was funded by IKS, Indian Knowledge Systems. The function of IKS is to showcase Indian knowledge to outside world. So what we are going to work on this one is the project title was Ahimsa Paramo Dharma. So that means that we should not kill. So how do we replicate the in vivo in the laboratory scale? So for example, so whenever you try to do in vivo, so you try to do with rat model, rabbit model, sheep model, and so on. So once you do these models, what is the basic fundamentals that you normally do is you just sacrifice them. I mean, say you try to kill them. So that is hinsa, that is what. So how do we mimic the same thing? So in the laboratory, can we do? So there is a technology called 3D microfluidic channels, which is predominantly a known technology for the mechanical engineers, may not be for biotechnology people, but predominantly for fluid and thermal people, it is always a known thing. So it was done at MIT, it was done at IIT Kharagpur, it was done at our lab. So many people do that one. So only thing is that how do you mimic that channels, arteries and veins and so on, so that no, you can replicate the same thing without killing the living things like rat, rabbit, and other things. That's why we just name it as Ahimsa Paramo Dharma, and we thankful to IKS, Professor Murthy Garu, and other people who evaluated our project. So my lab works on mostly into a lot of technologies. So micro machining, sustainable micro machining, nano finishing, bio nanomaterials. Always I tell, I don't know if some people are already old people, that I want to become a doctor basically. So 1998, when I graduated from the place near to the college which you are now, Annamacharya. So the village's name is Ennarpalli, Naramrajpalli, where I am a Navodaya student. I graduated in MIPC, Maths, Biology, Physics, Chemistry, but I wish to become a doctor. But my poverty sometimes, no, things you think in one direction, but some things may not be in line with your ambitions and aims. So at the time, I don't have 9,000 rupees to become a doctor. So, so I choose the path engineer, but however, I have ambition to become some doctor. So I did my PhD, and later I also married to a doctor. So it's all worked well. So I, however, why I said all these things is I love to work in bio, and nowadays students don't want to work in bio, especially mechanical students. So always they think fearful to the bio. oh, sir, it will take 5 years to do one cell culture, 6 years to, so we cannot get the papers. So that is not the thing. So one of the example that I would like to say is one of my student, Devara Venkata Krishna, he graduating, he is about to submit the thesis in this week, upcoming week, and he is submitting in 3.5 years with 15 publications. Out of the 15, 11 or 10 are Q1, remaining are Q2. Okay. So that is the potential of working into bio. So those people who are scaring to work in bio or other things, it's just a encouragement from my side that you need not to scare, but you just see at the look at the opportunity that you have. If you have good opportunities, you should grab it. So apart from it, we also work in additive manufacturing and smart manufacturing, so on. So this is what we try to work. We try to work on stents manufacturing. So stents gold standards development for BIRAC. That is the project that we have closed. This the project is on purely based on gold standards development. It is purely based on gold and stent development DS, drug eluting stents, and so on. So the polishing of implants and so on, lustrous and other things, biodegradable implants or internal fixations at the same time, lattice structures based implants, 3D printing, 3D bioprinting, and so on. We try to use. Okay, that is the gist of what we try to do. So sustainable micro machining, why we use sustainable micro machining is we try to do stents drilling and polishing of those micro holes for drug eluting stents, which I am not going to talk much. So the first part that you are seeing is purely the stents that developing by the commercial companies. But what is about the microorganisms growth on that one? That is the project that we received. And regarding that, what will be the drugs that we need to release? These are all the study that we have closed recently, the project. So normally we require three type of drugs. One is blood thinner, one is defatting drug, another one is antithrombotic drugs. When these drugs has to be eluted properly, and these are, yeah, so some of the intricate things are there. That is what about the first part. Second part, whatever you are seeing, nuclear applications, which you may not be, and third part is coatings as well as automobile applications and so on. So we have DT100i. Whatever you are seeing is the primitive version, but we have the advanced version. So DT100i stands for Intelligent Machine, Diamond Turning and Hybrid Micro EDM. It is the name, but it has a micro turning, micro milling, micro die-sinking EDM, micro EDG, micro wire EDM, micro drilling. And apart from all these things, we have another attachment that is called simultaneous EDM and ECM, which is a combination of electric discharge or I mean say electrochemical spark machining, which is a combination of EDM and ECM. That so just when come to the micro machining for biomedical applications or something, you can make any type of filters that you require. So you can see the micro turning, how we can make the electrodes for any type of applications and so on. And at the same time, you can see the pins, arrays. These are all are possible by this particular micro machining process. The minimum dimensions normally that we can make is less than 100 microns. Even what you can see is almost all 475 microns. At the same time, the hole that you are seeing here is almost all 10 microns basically. That means that 1 by 10th of a human hair. At the same time, you can see here, these are the high hard surfaces for lens, dies, and other things. These are the micro gears that we manufacture or the OEM manufactures for the watch applications, because sophisticated watches like Tissot or any other top brands, okay, Rolex and other things, they always use very high quality gears. So you require very high amount of precision and other things. Okay. Okay. So this is what our Tiny Technologies Lab works on. At the same time, as I said, we have one student who is working on one of the technology that is for wearable microneedles. This is the die that we manufacture using high-speed milling. This is a machining center by Kern Machining, and which is about the starting price of this particular machine is all about 5.5 crores. So where you can make the pins as a die, where this will act as a die, so that you will get the similar converse shape, so that no, you can manufacture the silicone pockets with a very sharp edges and so on. So this will be a template for making the pockets for drug eluting applications. Okay, later this patch can be put inside and on a surface, because if your whole sizes on your skin is 20 microns, if my tip, which is eluting the insulin or something, for example, for sugar patients or nothing. So if my tip is less than 10, 20 microns, you may not get pain because it is less than what the already existing hole is there. So this is how we try to work on it. So this is another thing that we are currently working for electronic printing and biosensor printing, which we are just started, but we are not experts in this area. So this is the one that I'm talking about, the attachment that we have, which is one of the best attachments. And I'm assured that commercial attachment in India, there is only one or two. So one of them is IIT Tirupati. Those people who are looking for doing a PhD, or if you are already doing PhD other places and you want to execute this one, for you it is getting the papers in Q1 journals and other things is very easy. So because the process is not well established by across the globe, this is called simultaneous electrical discharge chemical machining or milling, you can say, because our tool also rotates. Okay, so the surface roughness you can see here. If you do only microedium, this is the surface, normally 140 nanometers. I'm talking about very small area. So if you see the same area, I'm getting 22 nanometers. So this is a sophistication. At the same time, you can also get this particular surface on ceramics also. So make sure that these ceramics are partially doped so that no, you can get approximately a good value. Okay, so metal 3D printing that I'm just going to give you the glimpse that we try to work for the biomedical applications. We have EOS M290, which is again one of the costliest equipment that we have. So since Annamacharya is adjacent to us, which is an hour or 1.5 hour distance, so you can always come. So you can print knee implant, hip implant, shoulder implants, cranial implants, spinal implants, and so on. Currently, we do print spinal implants because it is easy to print. At the same time, less material is removed. I mean, say, very less material, powder material is required to print and do analysis and so on. So normally we prefer to have the spinal implants, and we are also working on acetabular sockets and so on. So how do we do? For example, if at all we want, this is generalized one because we cannot share the complete details. So cranial implants, for example, you can take the CT scan and normally you may get doubt how this blue one is decided. Normally you can just replicate on other side of the face, because always your face will be a mirror image of the next part. So you just mirror image so that you can get the part that you need to manufacture or something, so that no, later you can manufacture. Normally this you can manufacture with respect to metals, this you can manufacture with respect to hydroxyapatite and titanium and so on. You can also do lot of composites and other things, but being a there is a drawback sometimes you may face, because when you try to make other particles, for example, if I want to print with the titanium, I can print it because the companies allows. For example, if you want to mix with respect to some ceramic particles or something, so the company warranty will be a big problem. So yeah, we need to strike the balance. For example, if it is up to 1% or something that you can manufacture, you can manufacture. 1, 2, 3, 4, 5% is acceptable. If you want to print with respect to more amount of particles, like for example, I want to print with respect to copper particles, titanium particles, strontium, so on. For example, hydroxyapatite and so on. Hydroxyapatite will come under the soft ceramic. So the company may not accept because it is all the main thing is the laser and laser collimeter and so on. So there is a issue that you can also think. As I said, no, there are many implants that across the globe, many people are developing it. So what we try to do is establish sockets and textures that we are developing. And 1 minute, I'm getting a call. 1 minute from ministry. Yeah, so we work into the area of acetabular sockets. At the same time, we also work in the area of lattice structures. Currently, we work most of the lattice structures for some of the industries, and we also work for our students also. So, spine implant, as I was clearly mentioning, that we try to work mostly into the lattice structures for spine implants. At the same time, now we work for the so developing the spine implants is one thing. Later, we want to do the in vitro in vivo analysis because developing with only titanium is not a solution. So how much other materials that you are using, alloying it. Already Ti6Al4V is already an alloy, but with that alloy is sufficient is a question mark actually. So you try to balance with respect to antimicrobial features. You can have to balance with respect to anti-inflammatory. You have to balance with respect to antioxidants require antioxidants. So on. Because your patient may be overweight, your patient may be a sugar patient, your patient may be a BP person, and so on. So you need to check with respect to a lot of in vivo, in vitro, and other things. As I said, so the basic fundamental mistake the mechanical engineers normally do is whenever you get this type of surfaces, for example, if I want to do apatite layer analysis, this is fine. For example, if I want to do in vitro with MG63 osteoblast cells, in that circumstances, normally people again go to SEM analysis basically. So SEM analysis also look like this. So that may not tell you most of the details. In that circumstances, you need to go to fluorescence microscopy. So whatever you are seeing is a fluorescence microscopy of MG63 osteoblast cells on the coatings basically. It is once you do 3D printing, you also need to coating. That's why I'm just taking the reference of the coatings here. That you can see here, there are three things as a mechanical engineer we have to understand. One is whether the cells are growing or not, because the green portion that you are seeing is an actin filament, and the red one, which is looking like a orange one, because the green one superimposed red one look like a orange one. So because of that, so that is called nucleus. So the size of the nucleus determines whether the cells are growing or not. Point number one. Point number two, cell proliferation is taking place or not. So I mean to say the cell density, the number of cells per unit area, whether increasing or not, you need to understand. That is the second thing. The third thing that you can also understand here is that any foreign growths are there, like bacteria, virus, any other things are there. These are the three things that one has to normally understand. So when you want to understand with respect to these things, with respect to ACM, you may not understand. Okay. So that is about metals. Now we are working on the polymers and gels. So normal 3D printers that many people developing is we have a commercial printers. So many people develop all these things, but with you, you have a ABS or PLA, basic things. This will help you to make with respect to this biomedical thing, which may not be called as biomedical, but to showcase or to teach the bio students or medical students. This will be a great help for them. Even you can do with respect to like 30,000, 40,000, or 15,000 also you can get. So one of the best thing that normally our students try to do is orthotics. So for example, this is the project that we have submitted, but anyhow, we have not got the project. So however, we have some other funds to make it. So now we have made it, and at the same time, we have gone with a preliminary experimentation and so on. So this is another thing, as I said, no. So people can print this type of biomedical things with respect to a 15,000 or 30,000 small FDM machines like fused deposition modeling machine. However, the drawback of this one is that you may not use inside the body, but you can use this as a teaching aids for teaching, assisting things for a medical student or any other people. Okay. So we also have Form 3B with us. Form 3B gives us dental one or biomedical grades, which we have. For example, the only problem with this particular machine is that this will come with Form Wash and Form Sinter and so on. So uh, the only problem that I normally, because no, it looks very beautiful, definitely, but only thing is that you should be very cautious about consumables. So the consumables are very costly. If at all you want to develop the dental crowns in this one, you can develop zirconia based liquid is available that is predominantly can be used for this Form 3B. Nowadays, Form 4B also arrived. I think Form 4B and large size also arrived. This machine may cost you like 5 lakhs to 6 lakhs, but the liquid that you are going to get for a stereolithography is very, very expensive. Normal liquids are fine, but when you purchase this particular machine, you have to be ready for two things. One, the liquid that you need to purchase for regularly. Okay. And the second thing is you have to purchase from the same company because you need to put the cartridge inside. If you put with some other company, it may not accept. So always, if we are going for this particular company, you should have good amount of money in terms of consumables. For example, if you want to go with a zirconium based or dental crowns based ceramic slurry, I mean to say ceramic based photo curing material, as per my understanding, because I never purchased it, as per my understanding, the cost starts up 1.5 lakhs. I am still doubt about how much is ML or something, but maybe it is very expensive. So if you are purchasing like 10 liters or I think no, I mean say 10 cartridges. I don't know whether the cartridge is 750 ml or I think Sumant is there. Sumant Bhutoria is there. He may tell you when the question and answer time because he is a business guy. So I guess that is very expensive. Okay. At the same time, you need to have cleaning. So you need to have a cleaning liquid for biocompatible applications. So that is also again a cost incurring and other things. Okay. So think about when you are putting the investment and other things. So again, we have SLA based, for example, simple things you can develop by FDM printers or SLA printers. But we have with our collaborator with Statusys J850, as I said, where my wife is a student doing PhD. So they have a J850, which is a Statusys anatomical 3D printer that can print any type of colors. You can see here. So this is a beauty to teach the anatomy people. And anatomy is the difficult course in the MBBS. For example, those students, I don't know how many of you students are for MBBS. I don't know. So to teach the MBBS anatomy part, this is the beautiful thing that the people are doing here. Okay, you can see here lot of things. Fantastically, you can print colors at the same time. Most important is final finishing also. You need to do the final finishing of this particular implant. You can see how beautifully you can see the internal anatomical structures of these things. For example, if you see here, neck region, brain region, and so on. So this is a beautiful thing that I just borrowed from J850, which is our wife's research. At the same time, you can also print the graded lattice structures for anatomical models that you can see. Normally, our bone is very dense at the top surface and it is very less inside. So these are the things. At the same time, you can see multi-materials printing and normally J850 is a very expensive machine. J850, as per my little bit of understanding, it may start from above 5 crores. Okay. So it may be like if you want all the modules or the top end model that you may look, so it may cost you like 8 to 10 crores or something. That is what I expect. Okay. But there is another one, J55 or something, which is a smaller version that we are targeting now to procure. So that may cost around few crores, like 2 crores or something. Okay. So can we replace these anatomical models inside a human? The question mark is no. These are all our teaching models, teaching aids. So that no, it is very difficult for the some of the medical colleges that are coming to showcase the cadavers and to show every time cutting a dead body to show them directly is very very difficult, and at the same time students will be very very difficult to see at and other things. So gradual transition may be a better option. That's why anatomical models are nowadays becoming very very famous, so that they may not look at the body inside after cutting under directly. So gradual transition that they want to do. So 3D printing with cells, whatever you have seen till now is not a thing that is print with cells. So the initially what whenever we try to work with our own materials. This is called PLA nanohydroxyapatite. The PLA that we develop is stereo PLA. So we develop cancellous screws, cortical screws, Stillman pins, staples, and so on. So the bottom line of this particular story is that we know how to develop nanohydroxyapatite. We know how to develop stereo PLA. So with that, we have now ranging into hydrogels development and so on. Okay, thermal sensitive injectable scaffold. This is what our my wife is working. So this is a common thing that injectable based or extrusion based 3D printing people are normally works. Even Alfatek and other people also work. So you take the cells, you need to collect the cells, culturing it in a biomaterial solution, bioinks you can develop, bioprinting the skin, and so on. So that no, you can also develop. So we have not done much work on this area because As I said, students always fear. So we are about to procure this machine because of the our budget levels and the budget levels of the OEM are not in the line. So we are still working with the OEMs to convince. And we have one program on uh, third and fourth advances in additive manufacturing. We are getting the people to showcase their technologies because anyhow, selling is one company. Alpha, I mean, say selling is one company which is coming, and Status is another company which is coming, and so on. Other IIT Madras based companies and so on. So LAV, and there is another Korean company which I forgot, Kenstar or some company. So we are in touch with them. So this is how. So what we are doing currently with our printer is we have a printer without cells one, so which we print with the gels. Now we are printing the nerve conduits, nerve systems, and so on. Okay. So at the same time, as I said, we not only do that one, mostly our works will go with respect to the gels basically. These are the gels that we try to make basically. So normally people think that PLA is a very good biomaterial or something. PLA is a brittle material. So it may not work most of the time. So you need to blend it basically. For example, in this particular case, nano-hydroxyapatite is there, and PCl, PEG, PC, polycaprolactone, polyethylene glycol, and polycaprolactone based gels are there. And you can see here, it is called a tube inversion technology or tube inversion method that you can say. At room temperature, it is a gel. At 32 degrees temperature, it becomes a gel base. It is a liquid. Liquid to gel is called sol gel transition. At 37 degrees, this gel will become porous. Then inside the body, you have porous film, and male part and female part of the bone will grow together. So since the bone is an anatomy and it can grow together. Okay. So with that knowledge of gels, the knowledge of cells, MG63 osteoblasts, and we have some knowledge on cardiovascular cells because we are working with Sri Chitra Tirunal Institute of Science and Technology and so on. So now we are venturing into 3D bioprinting. Okay. So extrusion based 3D bioprinting, we are just started, but Luminex based things we are working. So for example, we don't have cells. However, we are working on, as you know, the technology of electrospinning and other things. So we develop a lot of Ayurvedic particles because we are having a university called SV Ayurvedic University. Whatever the particles that you want, we are fortunate that we can get from these people, and we can incorporate in it. Okay. So then you can extrude out of it, and you can check with respect to the cells, what are the cells that you want, and so on. Okay. So this is again, people are developing things. We are not up to the mark of what they are doing. So this is the latest thing that people are doing. Okay. So it is a motivation for not only for you, not only for us, not only for any biomedical guy. People are developing the livers, people are developing the artificial kidneys. There is again, uh, some people are developing artificial kidneys. That was I heard, but how far it is true, I also don't know, because kidney racket in a developing nation like India is a very big issue. So helping the poor people always a good thing and comes from my heart. As I was stating that I am also once upon a time a poor person, and yeah, still also we are lower middle class. So always it is a good thing that we develop for the people. Okay. So we develop uh, modern technology with respect to Ayurveda and so on. So natural medicine, we have aloe vera, we have turmeric, we have fruit-based nowadays. Fruit-based 3D printing, we are working for food actually, not for this one. ginger. So that this is some of the people are nowadays working with respect to all these things, which we are not working basically. At the same time, you can see here, I think we work with the nanoparticles in a PVA, curcumin solutions, and so on with our chemical engineering, where we want to develop some of the implants for the body, basically. Okay. Apart from it, many people are nowadays working on binder jet. We don't have binder jet. We were procuring, but things are not in our place. That's why, so we have couldn't procure. So there are fundamental things that binder jetting can do a ceramic implant. Later you can do dip coating and many coatings, and you can check with respect to bioreactor and other things. This is the same slide what we talked previously. So how do you collect the cells and other things which we are, and now I'm coming to our work. What we try to do is whatever we have is Luminex plus X plus basically. So this is whatever you are seeing just to show you the just a glimpse basically. So this is a Luminex, but whatever we have is a Luminex plus. So which we cost us around 30 lakhs with a 3-year warranty. Okay. So with that, we can print any type of models, any type of complex models. The beauty about this one is it works on the light basically. So the light, that too 305, 505 nanometer based light, you wavelength light that you can your accuracy will be very, very fantastic. For example, if I want to develop the contact lens, I can develop it because this is very, very accurate technology compared to your injection. I mean, say extrusion based. However, extrusion based has its own advantages, which Luminex cannot do, light based cannot do. Okay. So that's why now our purchase are already gone for one type of extrusion based, for not for biomedical, but yeah, for some other applications. So this is the one evaluation of various traditional Indian blood purification medicines using bioprinting microfluidic organ on chip for farms. That is what we are working with Professor Renu Dikshit, who is a professor and principal of Sri Venkateswara Ayurvedic Hospital, which is so as I said, Ahimsa Paramo Dharmaha and other things we are working on it. So importance of Ayurveda. Normally, if you see various diseases like heart attack, paralysis, and other things, these are normally because of the impurities in the blood, which leads to various diseases. Basically, this is one thing. On other thing, on other side, importance of microfluidic organ on chip. So evaluating Ayurvedic drug, eliminating animal testing. So the major thing is that we want to eliminate the in vivo. So for that, in this project, as a part of this one, we are developing the microfluidic channels, which are mimicking the rabbit model and sheep models. And we are doing the test in the rabbit model and sheep model at the same time simultaneously in the microfluidic channels also. So that no, we can compare this one. So as I said, we have Luminex Plus, so it can have a lot of potential in terms of printing any type of these type of channels that you can see here. So alveolar clusters, vessel exchangers, Hilbert curves. There are many, many things that it can do, and it can print very, very complex channels. That is for sure. So this is what a simple thing that I am showing you because I don't have permission to show the complete one. So one of the non-linear thing that we have got from the veins and artery system. So these are all the simple geometries. These are all not the simple geometries. These are the complex geometries. These geometries can be printable at the same time. Aspect ratio can be maintained and then we can flow this one. So what is the first thing that we are doing? Blood drawn from the patient. We are mixing with respect to the drug and we are sending it. So this is the first variety. And then we are doing incubation in a bacterial medium. And bacterial growth assessment using OD600 method and other things, you can just measure so that no, you can count before how many are there, after how many are there. So whether the blood purification has happened or not. Because if you can purify the blood, good thing about is that so this paralysis, heart attack, cancer, these type of things you can minimize basically. So one of the things that one has to understand here is these particles. Okay, Haritaki, Babitaki, Amlataki, these are the particles. These are the not the only particles. These are the basic particles because correct number or correct names we cannot give. So this will help us in mixing one of the powders basically. Okay, though for example, when you take a soap, you know that oils are used. Like that, these are the common ingredients. But main ingredients are other ingredients also there. So, and the most important thing here is that how do you extract the APIs from this? You cannot mix directly particles because when you try to eat this one, what will happen? This will go to your stomach and APIs will release to your body. So what do you mean by API? API stands for active pharmaceutical ingredients. Like when you take Dolo 650 or something, paracetamol will be okay going into the blood or something. Uh, Related to that chemical because I'm not a chemical engineer. That you so active pharmaceutical ingredients one has to extract out of it and then you need to treat with respect to the blood. So once you treat with respect to the blood, that you can understand how much. Okay, it is not that the particles directly you mix with respect to. That is a disclaimer that I would like to tell because you cannot. So there are methods to extract the API, standard methods that support we take from Ayurvedic college. Okay, so and we extract the APIs and those APIs are used in this one. So as a mechanical engineer that you can see here, so how the 3D printing will be done. First, we take the scan of the vessels and other things. We can do the modeling, this type of modeling, which may not be right. So model 1, model 2, model 3, model 4, but it will not work. So then we have, so once we finalize this one, then we have printed. You just watch it, the video, how we are printing it. So this is how the procedure of the printing, but it is done very fast. That's why you are seeing. So normally it will take 15 to minutes to half an hour time because whenever you want to print, this is purely printed at IIT Tirupati only. Okay, whenever you want to print it, you need to print at optimum speeds and the composition that you want to use and so on. Okay, so another one big challenge that we are facing is that we want to use our own fluids basically. So this is again a big challenge that we are working on developing our own stereolithographic liquids. There is one of the photo initiator which is not frequently available in Indian market, but yeah, it is available in the foreign market. So we are, my understanding is 10 ml of that particular liquid. So when we are procuring it costing around 50,000 to 60,000, 10 ml photo initiators and other things. So then, but later we found that that is not available in Indian market. So we are purchasing directly the liquids, complete liquids. Okay. These are the flow directions that microfluidic channel without blood and when the microfluidic channel with the blood and so on. So the what is analysis? What the analysis is, we have taken a control. Control means the blood with respect to our serum with respect to all the organisms. One side we have taken vancomycin and other one what we have used is therapeutic, whatever the used. In this case, whatever we have used is Staphylococcus aureus, which is a positive bacterium or microorganism that you can say. This is the control. One is control. The second one is vancomycin is added, which is again antimicrobial. So you can see here, it is also treating at the same time therapeutic, which we have used. It is also working, but compare, see, yellow is affected blood, basically, affected thing. For example, if it is becoming brown means that means that it is treating is happening. So brown quantity in the third one is slightly better. That is what. However, 2 and 3 are approximately same. In patient 2, for example, if you see here, so here we have used Staphylococcus aureus, which is a positive bacterium. At the same time, Pseudomonas aeruginosa. So normally it is gram negative. For example, here one is a control, basically which where we have not used anything. The second is with vancomycin. Still, it is in yellow condition only. But the third one is what therapeutics, which is called APIs. So that is what we have used. That is what clearly you can see here. Turbidity measurement we have done by optical density. That is called OD600 method. Normally yellow means bacterial presence and brown means no bacterial presence. We cannot say no bacterial presence. That means that bacteria is killed mostly. So the analysis shows that. So the one positive is it's fine, but when the patient is suffering from multiple things like positive and negative, so vancomycin is not fully handling it. So our therapeutics or Ayurvedic therapeutics are fine with that one. Okay, so these are the functional groups that we are analyzing and other things, and so this is what FTIR. And I request the organizers that we have yet to publish all this research. So this particular part, please don't share to anybody. So FTIR, functional groups and other things, and how this works. So for example, as I said, active pharmaceutical ingredients, we have two pharmaceutical ingredients. One is API is called gallic acid, which is inhibit the cell adhesion proliferation. Other one is agalic acid, which releases a reactive oxygen species, which create active stresses on the reactive oxygen stresses on the surface and which will kill the surfaces. So in this way, it will work basically. So coming to the non-technical part as an HOD, as my laboratory, as I said, we have finishing equipments, laser micro manufacturing setups. The second one, third one, as I said, micro tools. I said I have DT100i, which is this particular machine, and we have drag finishing systems, rheometers. We also work, as I said, one of our student who graduating now, submitting the thesis on purely on the biomaterials development, hydrogels development. He works mostly onto the rheology. And this is the Luminex Plus that we have. Bruker, we have 3D microsurface analyzer, 3D surfaces. And we have the filament extruders. We have a lot of filaments and other things. So ceramic 3D printers we have CNC, vertical milling machine, CNC lathe, 3D metal printer we have from UASM 290, and we have a tribometer from Artec, which cost us around 50 lakhs plus. And we have Iridium, which is a sophisticated research-oriented Iridium, the last one. So cut E350, which is from Agate Chalmers, which is again one of the world best company. So whenever you are thinking about a very complex shapes to cut, so you are most welcome. And this is again a 80 lakhs machine. We have the machinery. Okay. So I am very grateful to elsewhere that I'm handling as an associate editor for Journal of Manufacturing Process, which is Q1 journal, which is impact factor is all about 6.1 and 6.2. In between, it will fluctuate. Currently, I guess it is 6.1 now. So, so those people who are doing very good research, so you are encouraged to publish in this particular journal. And if whatever the support is required, we will do. And don't think that if the paper is rejected, it is the Ravi Shankar rejected or something. No. So we are the associate editors, and normally the rejecting will be done by a team. Basically, it is our reviewer team. Normally, we send to 5 people. Sometimes there are incidences where we send to 10 people also. Okay, so on. So this is the reviewers will take a call. Okay, and we also take a call definitely when there is a situation, narrow difference is there or something. So benefit of the doubt normally goes to the author only, definitely. I am very grateful to all the funding agencies that I started from IIT Guwahati with 5 lakhs. Then Baba Atomic Research Center about 23 lakhs. Then I got a big project about DST about nearly 1 crore. Then DRDL about 75 lakhs and IT, which is called Mighty, where we got 60 crores on theranostic therapy plus diagnosis. Then Imprint about 6 crores, 3 crores with IIT Kanpur and 3 crores with ISC Bangalore. These are the projects that I completed fully. These are the projects that I am the edge of completion. SCRB about 45 and BIRAC about 41, then SCRB CRG about 32 lakhs. And IGSTC is all about again a 6.8 crores, where I am a visiting scientist to uh, FRANUP for ILT, Institute for Laser Technology, where we work on advances in 3D printing technologies and so on. So these are some of the projects recently we received. Like Respond is about 32 lakhs, where we are doing composite 3D printing, and DST, STI Hub, STI Hub is not received, but we have received the project about 61, where we want to help the people around this particular region in the area of developing the poor, basically. So we have small project from TARE, ISRF, IKS, and other things is all about 56 lakhs. Whatever you are seeing, the last portion that I am targeting about that is a part and parcel of this particular thing. And we have cars project about 17 lakhs. These are the consultancy projects. And power grid, we have another 20 lakhs project. Apart from it, we also have TIH, Technology Incubation Hub on precision technology and positioning, which is about 120 crores. So one of the vertical is in this one is precision manufacturing. And at the same time, those people who are working in positioning and uh, precision technologies, you people also can apply. Our system works on a spokes. You can be like a hub and spoke model. Normally, we are a hub basically, 100 crores or something. So those people who works in this area like GIS, quantum clocks, so on technologies, which are related to precision positioning and other things, you can also get the funding from IIT Tirupati. Okay, so this is our research group that at IIT Guwahati, and we have another research group at IIT Tirupati. So with this, I am very grateful to Annamacharya in particular, my district people. So thank you one and all. And if you have any queries or suggestions or comments, I'm happy to take. Thank you.
Thank you very much, sir, for the wonderful insights into the research ongoing. And I would like to ask the participants, please use the chat box, post your questions, then we'll have a discussion. Sir will clarify the doubts that you have. Please raise the hand if you have any question to be asked. I will allow you to interact. Chitranjan sir, please unmute yourself and have a discussion, sir.
Yeah, they can introduce themselves because so that no, I will now come to. Yeah, please go ahead.
Yeah, good evening, sir.
Yeah, Chittaranjan ji, बोलिए.
Sir, I am Chitranjan Kumar Yadav, sir. I have already met you, sir, during that Impulse conference in IIT Madras, sir.
or laser? Uh,
Yes, sir, yes, sir, yes, sir. Yes, I
uh,
am working Samuel under Samuel, sir.
very good.
Okay, sir. So, sir, I have one doubt, sir. I am the first year student, sir. So, I have one doubt. I have so many paper that MG 63 cells and MC 3T3 cell. So, how can I decide, sir, which one we test over that substrate to test that biocompatibility? Means I saw in some paper MG63 cell is tested over the substrate, and I saw MC3T3. So how can I decide, sir?
It's all about, say, fundamentally, what we did is MG63, there are some constraints for us. First and foremost, no availability. Availability is the most thing. Second is economy.
Okay, sir.
Okay.
Yes, sir.
So आपके पास दोनों हैं, then you can use anything. But in our case, we have availability of only MG63, so we have used it. But we at the time, our literature was suggesting us MG63, so we have used. But anyhow, we take the support from biotechnology. Normally we take their suggestions. So now
Okay.
what we do is, because we are not the right people to take, because we do 3D printing and other things, we are master in it. But when it comes to the cells and other things, we go by the suggestion of the biotechnology, because it was done at IIT Guwahati. So we have a bioscience and bioengineering. We have people like Sachin, we have people like Lalit Pandey. So what they suggested, we followed actually. It is not that we don't have much knowledge on that one, how to choose or something. Say they suggested and we procured it.
Oh,
That is a Chittaranjani. That is a realistic answer. I can
okay.
say many things, but yeah, I don't want to lie it because I am not the right person to choose.
Okay. Thank you, sir.
But if you have availability of those things, if you have both availability, then you have to take the. See, you are from IIT Madras, you have biotechnology. So you speak
Yes.
to them, and I think you have in metallurgy, material science also. I think Sampath Kumar sir is there, T. Sampath Kumar. So
Yes,
he
sir.
regularly work in this area of research. So he may be a better person to tell what type of cells you can purchase or procure.
Okay, sir. Okay. Thank you, sir.
This impulse is again conducting by IIT Madras or any other place is conducting.
No, sir. That till now is not decided, sir.
No, it is there this year, 25.
No, sir. Till now is not decided, sir.
Okay.
Ravishankar sir, one question from Mr. Raghavendra Gaud. He posted in the chat box. I will read out, sir. Sir, how did you blend PLA and NHAP? NHAP is also brittle.
Hmm.
This is the question, sir.
So PLA and hydroxyapatite, normally that we blend with respect to micro extrusion basically. In micro extrusion, we have thermoscientific micro extrusion. You have multiple hoppers there. Normally, you can control the flow rate. So normally you blend, once you enter inside, automatically it will at the temperature, whatever we set like 180 degrees or 185 degrees or something, at the time PLA will become a liquid basically, and these particles will blend. So when it is in a solid form, it is a brittle one. It is not that much brittle. What I said, no, whatever we developed is not a pure PLA, but it is called stereo PLA. That is our patented product of IIT Guwahati, our laboratory. So that is the combination of two, three polymers basically. It is not the pure PLA because pure PLA will be very, very brittle. So, however, main ingredient is PLA. That's why we have written PLA. But whether it is pure PLA also, when you are putting into a micro extruder, so automatically when it comes to the temperature of 180 degrees or something, automatically PLA will become a liquid. So you can mix easily. There's no, I think it's a normal blending only. Hope I answered this question. Gaudaji, am I fine with answer or any other thing in connection with you? You want it?
Sir, he raised one more. Sir, is it for additive manufacturing FDM?
Additive manufacturing?
FDM, sir. Fusion deposition modeling. That's method.
No. Those implants we have manufactured by micro injection molding. Micro extruder and micro injection molding are come as a separate entity, but you can combine also because it come as a single set basically. So in that internal fixations we have done by basically by micro extrusion. We have not used FDM because FDM will not give you good surface. So you're talking about that implants one only, no? I think he's talking about this particular slide. These are all done by micro extrusion. These are done by micro extrusion basically. See, many things cannot be done by additive manufacturing because of economy basically. If you want to 3D print the same screw, it is very, very difficult for you. The surface will not be as smooth as micro injection molding. Is it fine?
Raghavendra, Raghavendra, sir, still if your doubt is not clarified, please unmute yourself and you can raise the question, sir.
Mic is muted, sir.
No, now you can try.
No, sir. Hello?
Audible, sir.
Sir, sir, you have tried micro extrusion, sir. Now I getting, sir, actually. I thought it is FDM, sir. Earlier I thought it's for
Because
filament you have made.
filament also we can make, definitely filament make and we do, but when it comes to the internal fixation device which goes inside the body, we cannot take the dimensions and other things because they are all ASTM standards basically. So surface finish will be very, very not good actually in FDM.
Okay.
So additive manufacturing, again a buzzword. It is people have to use wisely. Okay, so yeah.
Sir, one more question from Suchi ma'am. Could you please explain more about the preparation of PCL PEG hydrogel?
What preparation? See, you want me to tell the composition that you want or what type of the thing? Preparation means what? These are the gels you need to mix only.
Suchi ma'am, you
See,
can unmute yourself and ask the doubt, please.
see these gels basically. You need to mix the gels only. Polyethylene glycol, polycaprolactone, these are comes. You can make it gels actually. You can mix with the gels.
Ma'am, you are audible, ma'am. Please ask the question.
Hello.
Ma'am, you are audible. Please ask the question.
So I was actually asking about the formulation because in the slide it was mentioned PCL, PEG, PCL hydrogel.
This is
Hello.
yes, madam. Please go ahead.
So that was the confusion. Like twice PCL was mentioned. So I just wanted to know the
So,
formulation.
so you need to use twice actually. For example, if you are using PCL, PEG, PCL, so that is a structure that we want. So when we are trying to see, I would say 2 units of PCL, 1 unit of PEG. Once you do the FDA analysis and other things, how the structures are forming, and based on that, we normally formulate that. Anyhow, the compositions is almost all double. First, point number one. Point number two is how the structures are forming. Another thing, chemical structures are forming. Another thing is what we decide.
Oh, okay, okay.
So
Okay, sir.
once you do the functional group analysis and other things, no, FTIR, you do visible spectroscopy, Raman spectroscopy with PL and other things, no, automatically you will come to know some of the details. That's why we named it as like that, madam.
Sankar, sir, you can unmute yourself and you can raise the doubt, sir.
Good evening, sir. This is Dr. Sankar, Assistant Professor from Indian Maritime University.
Yes, sir.
Sir, I have a small doubt about this capacity of this additive manufacturing which is existing right now. Can we synthesize any gradient additive manufacturing? Means my surface should be a ceramic, whereas base metal should be a metal for bioimplant applications.
You may not use additive. See, I mean to say for flat surfaces you can do. Simple surfaces you can do. For a cylinder, flat surface you can do. But for a implant, you have to do 3D printing of metal, then you can go for dip coating or this type of any other coatings.
Yeah, we had that experience of developing coatings, ceramic coatings for metal implant applications. But I'm thinking whether it is possible in future, maybe in nearby future, that we can synthesize a gradient additive manufacturing technique so that we can
There
synthesize.
are nowadays technologies for multi-material 3D printing. As such, I never worked in that area. But we have two independent one. I have ceramic 3D printer separately and metal 3D printer separately. I don't have a combination of it. But when I want to add this ceramic to the metal, company people are not accepting. As I said, no, when I was explaining US M290, so the company people will not accept because warranty will be invalid. So that warranty will come almost all with 10% of the cost of the machine. For example, machine cost is 6 crores. 10% is a huge amount. That too, I have a 3-year warranty.
It's okay. And
So,
I have this doubt whether in future it may be possible
yeah,
with the
in
one
future it will come. In future it will come. So by and large, people are doing on a flat surface. For example, I have already implant surface. On that implant surface, so I can do the ceramic. If I want to do for example, I have a titanium knee implant or any implant is there. I want do coat a hydroxyapatite. You can coat it because you can do it definitely. There is no problem for it. But you say functionally graded in that circumstances, that means that you want to gradually transform from titanium to hydroxyapatite.
No, my
That
case is different from titanium to titanium oxide.
okay, titanium to titanium oxide you can do because again it comes under a soft ceramic. Yeah, better is that you do coating only, sir. I think you can use PVD or something.
No, we are using all these coating techniques, plasma electrolytic oxidation.
But 3D printers, as per my knowledge, I am unaware because I cannot say no, but I am unaware. So you are from which institute?
Actually, I did my PhD in NIT Tiruchi, where we used to develop this plasma electrolytic oxidation coating, which is actually kind of conversion coating. Metal, the surface of the metal will get converted to metal oxide.
So you mean to say that titanium nanotubes will form and other things?
No, not exactly nanotube. In the case of anodization, there will be nanotube formation. But in the
There is
case
one
of plasma
faculty,
electrolytic
in chemistry.
oxidation, which will happen at higher voltages. So it
Okay.
will develop a thick and adherent ceramic coating.
Okay. Yeah, I am not expert in that area, so yeah, you have to teach us. Yeah.
Okay, okay. Okay,
I know about it, titanium nanotubes and other things. Some people do. So we also do because. Mm. Yeah, yeah. Please go ahead.
no, I haven't told anything, sir. I think maybe the
Somebody, yeah.
yeah.
It's fine, fine.
Okay, sir. Thank you.
Thank you.
Dear participants, if any more questions are there, please unmute yourself and you can raise the doubt. Sir will clarify your doubts. Abhishek sir, thank you very much, sir, for the wonderful presentation. And you have given some enlighten us towards the biomaterial and the research in many ways, like micro machining, then 3D printing. Thank you so much, sir.
Thank you, Dr. Ajay. And so, how many participants do you have from across India? How many are from
Sir,
Andhra?
apart from 20% of our own institute, the remaining are 100 members, sir. Total 123 participants are there, sir.
Oh, you have a good number.
Sir.
So, next talk is by?
Sumant Bhutoria, sir. He's from
Yeah,
3D
I know
printing
him.
industry, sir.
I know him. I know him. Yeah. He
Yes, sir.
know me. He know me
Yes,
from
sir.
IIT Guwahati days.
Sir.
Yeah, he came to IIT Guwahati.
Okay, sir.
सुमंत जी कैसे हैं आप?
I think sir is about to join, sir. Still time is there. 10 minutes, sir.
He was there. I think when I started my session, he was there.
Okay, sir.
Okay, so those people who want to connect, I have given my details. So those people who are, time is there. Sumant has joined. You say hi to him and then
No, sir, he's not there, sir. Just a
not
minute
there.
back, he called me and he will be here after 5 minutes, sir.
Okay. So what are the other institute that you have? I think major institutes.
From participants, sir.
Hmm.
Nearby college, RGM set, then G Polarity, and from north also there are a few members, sir.
Good and best wishes. What is the talk on by Sumant Bhutoria? Team development. What he is going to talk?
Sir.
Okay. Anyhow, Sumant joined.
Not it, sir. Topic is, sir, advanced techniques in 3D bioprinting.
Mhm. Good. Okay. So thank you and wish you all the best. Okay.
Thank you, sir. Thank you
Thank
so
you, sir.
much.
Thank you.
Can you see me? Can you hear me?
Yes, sir.
Okay. So should we start?
Just a minute, sir. A minute back, Ravi Shankar sir left the meeting and he asked you about you.
Oh, I see. Oh, okay.
He wanted to say hi to you, sir, but unfortunately he left.
Okay. Sorry about that. So we'll connect again sometime. Let me share my presentation.
Sir, just a minute, sir. Our colleague would like to introduce about you. So
Sure.
after the
Sir, good evening, sir. This is Ajay Kumar, Assistant Professor, Department of Mechanical Engineering, the coordinator of the FDP titled Advanced Biomaterials for Orthopedic and Tissue Engineering Applications. Dear participants, before going to the next second session of our third day of FTP, I would like to introduce Sumant Bhutoria to you. Sumant, Mr. Sumant is an entrepreneur working in the exciting field of 3D bioprinting, medical and industrial automation, and other rapid prototyping technologies. Alfatek Systems is the market leader in 3D bioprinting in India, builds customized and reliable 3D printers and medical R&D equipment, and works with the biggest R&D institutions like AIMS, IITs, CSIR labs, and the largest Indian engineering companies ITC, Tata Steel, L&T. Alphatech has been featured multiple times in media outlets like Times of India, Dainik Jagran, CNBC TV, India Today TV, etc., and has been selected amongst the top 10 startups in IIT 2020 Startup Spotlight organized by Pan IIT USA. Sumant currently works as a CEO and a founder at Alphatech Systems, and together with his team, he has played an important role in making Alphatech synonymous with the quality and reliability in more than 250 R&D labs in India. In his previous corporate avatar, Sumant has worked in US, Europe, and Singapore in various engineering, management, and finance roles. In his last corporate engineering role in Virginia, USA, Sumant worked in product engineering at Micro Technologies, a $21 billion US manufacturer of DRAM and NAND flash chips. Sumant ended his formal education with an MBA from IIM Ahmedabad and was an institute scholar ranking in the top 3% of his class. His master's thesis in electrical engineering at Arizona State University, USA, led to an IEEE conference paper on VLSI CAD systems for portable battery devices. He completed his BTech in electronics and ECE from IIT Kharagpur. Sumant has co-authored more than 4 international journal publications in 3D bioprinting and serves as a reviewer in various journals from Taylor and Francis, SBAO, Academia. He also plays an active role in various Indian government initiatives like SIH Hardware Hackathon and is an organizing committee member in IIM Alumni Kolkata chapter. With this brief introduction, I would like to hand over the platform to Sri Sumant Bhutoria, sir.
So, first of all, a big thank you to the organizers and thank you for the warm introduction that you gave me. To all the participants who've come here, I look forward to sharing the next 1 hour or so with you, my knowledge, my experiences in 3D bioprinting. And finally, thank you to the funding agencies who've allowed this particular forum so that we can all interact and share our knowledge together. So can I share my presentation? I think the organizers, if they can allow me, if the option is not here, I think.
So you can share, sir. It is, you are there as an organizer.
Okay, because the share button here seems to be disabled and it says only meeting organizers can share. Let me see if there's any other way. No, for some reason Is there any method there in your which allows me to share? Because it says only presenters and organizers can share. So maybe I'm not logged in as a presenter.
Will you please try it now, sir?
Now I can do. Okay, hold on then. Okay, so let me share my entire screen. Okay. Can you all see my screen now?
Yes, sir.
Okay. So the slides are visible now?
Yes, sir.
Okay, good. Let me just start the slideshow here. All right. So so this is my company, Alfatek Systems. We are India's largest 3D bioprinting company in terms of the number of installations. We've been around for about 12 years, and during this time, we have set up and installed our various 3D bioprinters and 3D printers and various installations in all parts of the country. So from Srinagar to Trivandrum and from Baroda in Gujarat down to Guwahati in Assam, we have completed a number of installations. The company was founded by me about 12 years earlier. I think the organizers have already given a warm introduction about myself, but very briefly, we have over a period of 12 years, we have built up a presence in more than 250 labs all over India. We are bootstrapped, so we've not taken any funding from any agencies. This allows us a lot of operational freedom in terms of serving the customers that we like and moving in the direction that we like. So we don't have any of the pressures from the investors to generate revenue for the heck of revenue. So as some of you may have started a company or have had previous experiences, having investors on board puts a lot of pressure on you in terms of trying to generate revenue and profits. Whereas in our case, since we have not taken any funding, we can focus on our work. My passion has always been in 3D printing, 3D bioprinting, and the freedom of being able to run my company without any interference from investors allows me to focus even on projects that may not be profitable in the short term, but may have a lot of scientific implications. Okay, I run my company with a very strong ethics and business principles. We've always put the customer up front. So no matter where we have gone, we have done our best to provide full support to our customers. We've had a number of R&D collaborations with a large number of universities. We have, in times, we have worked on some of the projects together, and this has also helped us in publishing various R&D articles in various journal publications and so on. So just to tell you some of our prominent clients, they are AIMS, New Delhi, ISC, IITs, then various central government institutions like SCTIMST, which is one of the best 3D bioprinting institutes in India, then NCBS, CSIR labs, ISRs, NIPERs, BIT, NITs, and various private universities like VIT, Vellore, Manipal. Incidentally, I am at Manipal today. So we have certain meetings tomorrow, and I am doing this presentation from my hotel room. So that's the big advantage of being online, right? I mean, you need not be present at the venue, and yet you are allowed this forum in which you can share your information with people all over the world. Uh, we've also worked with a number of pharma companies like Alchem Labs, Sim Labs, and so on in the course of 3D printing tablets, and also with various hospitals like the Manipal group, the Tata Cancer Hospitals, and various such hospitals in order to help in various 3D printing initiatives that they have. We also work with some of the best companies in India, be it in engineering, Tata Steel, or in FMCG, ITC, or various other types of organizations. Okay. Now, before we move further, I just want to give you a brief overview of the entire 3D bioprinting workflow. Okay, so what exactly is 3D bioprinting? This may be somewhat new to some of you. I had asked the organizers before, and they told me that we have faculties from various departments in mechanical and various other departments, and some of them may not be very familiar with what is bioprinting and what does it mean. So in this slide, I will try to explain to you a little bit about what is 3D bioprinting and how do we go about this entire process. Okay. Uh, just before I move forward, are all of you comfortable? Are you able to see my slides? Can you hear me properly? Everything okay? Organizers?
Okay, sir. Everything is fine.
Yeah. Can someone respond? Can you guys hear me?
Yes, sir. It's audible, sir.
Hello.
Audible, sir.
Yes, sir. It is audible.
Can someone from the organizing team just respond, please, and confirm that everything's okay?
Yes, sir.
Everything is
Everything
okay,
is
sir.
okay.
It's audible, sir.
Or maybe, okay. Hello. Oh, okay. But everything's okay, everyone? Okay, all right, fine. Okay, sorry guys, I just wanted to get a confirmation that everyone could hear me, and the organizers just called me and said everything was fine. So, all right, so sorry for the small break, and we'll just move forward. So in the 3D bioprinting workflow, we start off with first the CTA or the MRI scans. So the affected patient or the person who has some injury or illness or has some fracture or some tissue damage, we will take their CT and MRI scans first. And then from the CT MRI scans, we can process this into various 3D CAD models. Okay. Now, there are various softwares that are used. There are some open source softwares, and then there are paid commercial softwares. And later on, if you guys want to work on it, you can reach out to me and I can help you with some of the softwares that allow you to convert patient-specific CT MRI scans into the 3D CAD models. Okay. And then once we have 3D CAD models, which you can see in the second phase here, what we will do is we will try to reconstruct the affected regions and isolate them. And in some cases, we may want to create some appendages, or we may want to add some appendages there, or tissues that we want to kind of create, or remove the damaged portion and recreate the actual or the printed or the realized type of tissue. And then for doing that, we again use various softwares, and then we also use these 3D designs of the regions and try to make pre-surgical models. Okay. Now, to create the pre-surgical models, these are basically models of the affected region. And for this, we can use normal 3D printers. So for example, FDM or DLP based 3D printers. Okay. So we have various such printers available from Prusa or from my company Alfatek, and you can use this to create the pre-surgical model. Now these models will always be in various plastic or resin. Okay, so not the real living tissue, but more in plastic or resin, and these are just models so that people can visualize or see the affected region. Okay. Once we have the pre-surgical models and the doctors can figure out what needs to be done or what needs to be changed, we start focusing on the affected regions and try to 3D bioprint it, 3D bioprint the appendages or the affected regions, okay, with the living cells. Now this is done with 3D bioprinters. Okay, so you can use various bioprinters, the Anga series from our company or the Arjun 200 from Region Home. So various such bioprinters are available. So you can use this to actually make a small model or a tissue patch or the affected region. Okay, and then once we have this 3D bioprint affected region, we will put it in a CO2 incubator and then allow it to grow and form the particular tissue that we want to put. And then in the final stage, we will go ahead and implant them into the animals, okay, for seeing whether whether the particular appendage has helped in recovery of that particular damaged tissue. So for this, we obviously need a hospital or a surgery room setting, and we have various facilities in a number of universities for doing that. So this is the entire 3D bioprinting workflow. Okay, so starting from the CT MRI scans of the damaged areas down to the making the pre-surgical models, then the 3D bioprinted models, and finally implanting it back into the animal so that you can study how the implant has helped in recovery of the damaged tissue. Okay. All right. So for our 3D bioprinting, my company builds various bioprinters, and we are also partners with a number of reputed European and American manufacturers of both printers and bioinks. So within the 3D bioprinters, we have our Anga series of bioprinters, and then we work with a company called Brinter, which is a Finland-based company, and they make some mid-range 3D bioprinters with a lot of different print heads and accessories that are available. And then with another company called Readily 3D, which is a Switzerland-based company, and they work with volumetric bioprinting, which is again a very advanced or a very interesting emerging field. So here we can 3D print an entire volume all at once. So within a few minutes, the entire living cells that is present in the media can be 3D bioprinted. Now, this is very exciting because in a normal bioprinting kind of setup, it takes several minutes or sometimes even hours to kind of print 3D bioprint the affected region or the model that we want to make. Whereas in volumetric bioprinting, available with Readily 3D, we can make the entire construct in a matter of seconds or minutes, right? And then we also work with another company called RegenHU, which is a Switzerland-based company, and they make the world's most advanced 3D bioprinter. Okay. Within the bioink space also, we manufacture some of the basic inks ourselves, and we've also partnered with a number of companies like Tata Steel, and then with Tata Steel, we market their hydroxyapatite, which is used in bone and cartilage modeling. We work with a company in UK, which is Manchester Biogel. So we market their peptide-based inks. And then another Finland-based company called UPM Biomedicals. And here we market their nanocellulose-based inks. Okay. We've also recently tied up with Sri Chitra, SCTIMST, which is, as I said, one of the best bioprinting institutes in India, based in Trivandrum. And we are marketing their Gelma-based inks. Okay. So coming back to our company again, the Anga, which is our flagship 3D bioprinter. So this is a second generation model. It is the world's first 3D bioprinter with liquid spill protection. So meaning that in our bioprinter, there are no electronics or any sensitive mechanical bearings, which is housed below the print bed. Okay, so this is very useful because in bioprinting, we are working with various pastes, inks, and so on. So in this particular case, there is always a chance of accidentally spilling some of the inks or the liquids onto the print bed, and this can potentially damage the 3D printer. So we took the inputs from our customers and designed our machine in such a way that there are no electronics or mechanical bearings below the print bed. Okay, so in case there's any spillage or anything, you can simply wipe off the liquid and none of the electronics or mechanical components will be affected. Okay, we have in our 3D bioprinter a number of different types of extruders. So there is syringe pump based extruder, pneumatic based extruder, or hybrid extruders. And I'll tell you a little bit about this because in bioprinting, it's very important to understand the difference between the various types of extruders. So on one hand, we have constant volume type of extruders. In a constant volume extruder, which is also a syringe pump based extruder, we are always guaranteeing that there is constant volume of extrusion throughout the printing. Okay, so in a constant volume, your pressure may change a little bit inside the syringe, but the extruder always ensures constant volume that is extruded out. Okay, this is very useful because in a bioprinting setup, you cannot have ununiform or non-uniform type of extrusion, because if in one part you have more cells, in the other you have less cells, when you put it into the CO2 incubator, the living cells will not grow uniformly. Okay, so that's why a constant volume or a syringe pump setup is usually the most preferred way in a bioprinter. Sorry.
Fresh menu.
Sorry, any questions?
No, sir.
Okay, all right. We'll move forward. So as I said, there is the constant volume type of extruders, which is the syringe pump, which ensures constant volume of extrusion. The other type we have is the pneumatic based extrusion. So in pneumatic based extrusion, which is also called constant pressure, here what we have is we have a constant pressure which is exerted on the syringe liquid contents, and as a result extrusion happens. Now in a pneumatic setup, the advantage is you can get very good control over the start and stop. But the disadvantage here is that you may have non-uniform extrusion. This is especially true if you have a colloidal or a heterogeneous type of solution, or in case you have a large syringe barrel, which means that when you start at the start and at the stop, the volume of liquid that is supposed to be extruded, the friction between the liquid between the walls ensures that a small difference in the volume of extrusion happens between the first drops and the last drops in a 3D bioprint. Okay, and then we have something called hybrid extruder, and I'll talk a little bit about that. In hybrid extrusion, you will have the advantages of both a syringe pump and a pneumatic setup. Okay, so you can get constant volume, and at the same time you can get good instantaneous stop and control over your extrusion. Okay, so in our printer we have all these three different types of print heads. We also have the temperature control in terms of both cooling and heating. We use Peltier or electronic based temperature control to ensure that the longevity and robustness of the entire temperature control hardware. We use steel linear movement, and we use dual steel rods to ensure that there is a stable, precise mechanical movement. We have standard features of HEPA filtration and blower fans, and also a very powerful 10-watt UVC germicidal lamp to allow complete chamber sterilization. We also have single touch calibration and a very simple and powerful software suite to take care of all the design formats, from CT, MRI, DICOM files to 3D, CAD, STL, OBG files, and so on. Our 3D bioprinter is constructed with high quality anti-corrosion SS304 and aluminum metal chassis. and it has a small compact footprint so that you can house it in any standard biosafety cabinet. Okay. The other, apart from the 3D bioprinter, the 3D bioprinter that we have allows you to work with a number of various advanced accessories. For example, our bioprinter, you can combine electrospinning with bioprinting. Okay, so normally you have either instruments that can do electrospinning or you have standard bioprinters, but you don't have an instrument that can do both, that is electrospinning and bioprinting. So in our machine, we have enabled this kind of a feature through a module. This was developed with Professor Dhara at IIT. And with this feature now, our Anga 3D bioprinter will allow you to fabricate consecutive layers of electrospun fibers and bioprints. Okay, so why is this important? In our body, the living cells exist in a extracellular or ECM matrix. Okay, so in this matrix, or the protein structure in which the living cells are all housed, it is the natural environment for the living cells. Okay, now in order to mimic what we have in the human body, the only way to make this kind of ECM matrix is through using electrospinning. So with electrospinning, you can create a very dense network of nanofibrous fibers, and within that kind of mimics the ECM of the human body. And then if you do one layer of electrospinning, you have created a matrix, and then the second layer you do bioprinting with the living cells, so the living cells can go and enmesh within the fibers. And when you do this a number of times, you are able to better mimic the ECM matrix in our body. Okay, so this electrospinning and bioprinting is available in very expensive machines in Europe, like Region U, but it's not available in other type of 3D bioprinters. So within India, we are definitely the first, and probably in Asia also, to provide this powerful capability of doing both electrospinning and bioprinting. Okay. The next feature that we have in terms of advanced bioprinting, we have the feature of hybrid extrusion. Okay, so here we use both pneumatic and syringe pump capability. Okay, so this is a printhead that is developed by a company in Germany, and we have used their printhead. So in this, we have both a pneumatic inlet through which air pressure can bear down on the plunger for providing pressure for highly viscous type of inks. And at the same time, we have a lead screw which is driven by a stepper motor, or with something which is similar to a syringe pump setup, which actually controls and ensures that constant volume output of the inks can happen. Okay, so as you can see in the picture, you have both inlet for pneumatic as well as the lead screw, which is actually driving the ink out from the nozzle. And here in this picture, you can see very fine extrusion of the ink on whichever pattern that you would like to make. The other advantage of this hybrid extruder is that it allows you to make micro droplets or inkjet based arrays with up to 1 millimeter spacing between drops, which we have achieved in our printer. And this also ensures very reliable and precise droplet size in the array of micro droplets. Okay. The next advanced feature that we have is something called 3D bioprinting of blood vessels or stents in something called a rotating spindle or theta X mode of operation. Okay, so here we have a rotating spindle. So you can see the spindle, and the extruder is actually printing on that spindle. Okay, so you can see this process here. So we are making a complex stent here. So the spindle rotates, and we can control the direction of rotation. And the extruder is also extruding ink and also moving, so it is creating a kind of pattern that we want to make. And in this way, we can make very complex stents, and of course we can also make standard types of blood vessels or cylindrical vessels, or we can model thoracic vessels, we can model small intestines, and various such cylindrical objects that we want to do. Okay, so in this process, basically, this is something that is very unique to our bioprinter. I have not heard of other companies able to provide this, but this allows you to create long cylindrical vessels. In a regular Cartesian type of 3D bioprinter, as you begin to make the larger cylindrical vessels, just due to the sheer weight of the inks, the whole structure will collapse. So it's very difficult to make more than, say, about 5 millimeter or 10 millimeter of a cylindrical vessel. And the geometry of the cylinder is also not maintained. But using this type of method, in which we are printing on a rotating spindle, we can create very long cylindrical vessels as much as we want. We can change the diameter by changing the rotating spindle diameter, and we can also create very complex patterns. Okay, so this particular setup was used by IIT Delhi, and they have filed a number of patents on this. And a number of people, groups are working on this at NIT Suratkal, IIT Delhi, also at IIT Kharagpur, and number of papers and interesting publications have come out from this kind of a system. So just to give you a brief historical background, this is what our first printer looked like. This was about 10 years back. So this was a single extruder. But as you can see, this is how we have evolved from the Alpha 3D bioprinter to our current Anga 3D bioprinter, which is much more stable, robust, with a large number of features. Okay. All right. We also have various bioinks and various accessories for the lab. So we provide PCL, gelatin, chitosan, alginate, and then we provide all of this to our customers, along with various other inks from our partners, like hydroxyapatite or peptide-based inks or nanocellulose. Broadly here, when you talk about bioinks, just to tell you, there are various cross-linking techniques that are used for polymerizing or solidifying the liquid inks. Okay, so there are three techniques broadly that we can classify them under. One is chemical cross-linking. So here we use various cross-linkers together with the actual bioinks. So say, for example, alginate. So alginate gets cross-linked with calcium chloride. Similarly, for various other biomaterials. The other method for cross-linking is using photoactivation. Okay, so here we use UV or some other blue light to photopolymerize the photoinitiators that are put in the bioink. So various photoinitiators are available, like PEGDA or DAP or LAP, and various standard inks have now been developed, like Gelma, which can get photocured and which can be used for bioprinting. The other technique that is sometimes used is thermal for collagen or gelatin, which use a gelation temperature. So if you change the temperature, you can change the state of the liquid from liquid to semi-solid. Similarly, we can also use pressures in the case of peptide-based inks. So when you apply pressure on peptide inks, they will change from semi-solid to liquid, and when pressure is removed, they again become semi-solid. Okay, we've also developed various accessories like the Alpha UV Cure, which is a portable high-powered 10-watt UV LED system for photo curing. We've also developed something called a Alpha Chem Cure, which is basically a vaporizer or a very simple bioincubator, if you like, where we can introduce various vapors or create a very controlled climate inside the chamber for long periods of time. Now let's talk a little bit about some of our projects that we have done. Okay, so you might have all heard about 3D printed tablets. So 3D printed tablets are again something that is started in the last couple of years. The idea here is that just like in the olden days, where our older our natural Ayurvedic or doctors would actually make the medicine using various herbs and various other materials. and depending on the disease, they would make that particular medicine and give it to the patient. Okay, so every patient and every disease would have the medicine customized to their as per their choice. So now, though, in modern medicine, we all have mass-produced tablets. Okay, so if you have a headache, whether it is severe or whether it is a very mild headache, the doctor will still give you, say, the same similar doses of aspirin, right? Now, imagine if it was possible for the doctor to have various doses of aspirin, various power levels. Okay, then maybe he could have given you the dose that is appropriate for your headache. But because in the market only few standard powered and dosage levels are available, he is forced to give you the medicine which may be more or less than what is required for you. So in this context, 3D printed tablets come into picture, where they are considered to be more customized as per your requirement. So the idea is, with 3D printed tablets, the doctor can can fabricate these medicines at the clinic at the particular dosage that is required for your disease. He can also try various conventional techniques and even new novel techniques to vary the dosage patterns. So in case the medicine is supposed to be given to you at very specific periods of time. Okay, so it's something called a pulsed duration, or if it has to be the medicine has to be given to you in your body after in a constant manner, so constant duration kind of tablets, or else if the tablet or the APIs need to be given to your body affected region in one go, which is called instantaneous dosage. So for all of these different dosage, we can 3D print tablets of various sizes, shapes, with various infill patterns to ensure that you can get the appropriate dosage and appropriate power level for that particular tablet. Okay, so that's the idea for the 3D printed tablets. And this is work that we've done together with a pharma company, Zim Labs in Nagpur. And here what we did was, we started first with our 3D bioprinter, and then using this 3D bioprinter, the pharma company was able to develop the specific recipe that is required for 3D printing tablets on the placebo films that they had. And then once this was standardized and the recipe was perfect for production, the same was introduced into their pilot production line. So here you can see that our particular extruders are being set up on the pilot production, so that we can make the 3D printed tablets in commercial production. Okay, so again, this is another application area, something which is very interesting. If some of you would like to work in this area, please contact me and I can certainly help you in your domain of research. Similarly, we've done a number of projects with Tata Steel. So there is 3D printed polymers for medical implants. We worked with various types of polymers which can be used to substitute for metal. Again, I cannot talk too much about this, but this is again an area of research that we worked for commercialization. Then similarly, in medical device, we've worked with them for self-assisted laryngoscope, which allows the doctor to provide larynx procedures in a self-assisted manner without the need for additional technicians. Okay, and then currently also working with them on digital stethoscope, so that the device can be used by doctors to listen and examine heartbeats. We've also worked with various R&D institutions. So here I'll talk about a little bit about our project with Sri Chitra Trivandrum, something we've done about 7 or 8 years back. So here we used our 3D printer and then we customized it into 3D bioprinter. And then we have done various studies on the printability of the inks, and also studied the 3D bioprinted constructs and check it out with that of a professional expensive 3D bioprinter like Regen HU, which costs about 2 crores. and then we are able to characterize and also study how we can improve the quality of our printer, how we can use various inks and use this study the printability of these inks. So this is a very interesting paper that has come out, and we have shared that in the open domain. If some of you are interested, we can share this paper with you, and I encourage you to read it, which will help you in your research if you'd like to focus in this particular area. Um, these are various work that we've done with various agencies, our testimonials, engagements. Uh, we have various journal publications where I am a co-author as well, and I am also a reviewer in various journal publications. I try my best to contribute to the community, 3D bioprinting community and research. These are some of our recognitions and our achievements. We've been featured in CNBC TV 18, in TV, also in various newspapers and agencies, Times of India, Dainik Jagran, etc. And we've also done work during COVID, and also featured in our IMA Ahmedabad magazine. So this is broadly some of the experiences that I wanted to share with you, that we've had in the last 8 to 10 years. If you have any questions, or if you'd like to ask me any question in the slide, please feel free. If you'd like to contact me, this is my mobile number, this is my direct number, as well as my email ID. You can note it down and reach out to me as you like. So here I end my presentation, and if any of you have any questions, or if you'd like to ask, I open the floor for that.
Participants, you can unmute yourself and you can ask any doubts if you have. Sir will answer the questions. Please unmute yourself. Mic is allowed to all of you. Unmute yourself and ask the questions.
So did you all enjoy the presentation, or did you learn something from this presentation, or is this somewhat relevant to your research area as well?
I think our participants enjoyed a lot with your presentation, sir.
Thank you.
I have few doubts, sir.
Yeah, please go ahead.
Is it possible to print silicone material?
Yes, it is possible to print with silicon. So silicon is quite viscous, and because of that, what you have to do is you have to change the parameters of your extruders to allow for that. Now, one option, the most popular option that people use is to use a pneumatic-based extruder. So in a pneumatic extruder, you can go up to 7 bars with most commercial printers. I mean, the low-cost ones come at 4 bars of pressure, but with the more expensive ones, you can go up to 7 bars. And in some cases, you can even customize and increase that to up to 10 or 12 bars by making certain suitable modifications. And using that, you can print with various viscous type of silicons. Now, within silicons, it depends if you are using an exotic mix of silicon, or if you have some additives in your silicon. If your bioink of silicon is not completely homogeneous, then you may have to use something like a hybrid type of extruder, because what we find is in pneumatic extrusion, where your solution is not homogeneous, the volume extruded may be different. So in places in your bioink where your solution is more viscous, a smaller amount of material gets extruded, whereas in those places where it is less viscous, more material gets extruded, because in a pneumatic setup, the pressure is constant. So in this kind of setup, it is preferable to use a hybrid type of extruder, where the pneumatic pressure is helping to extrude, but the actual extrusion happens with lead screw, which ensures that you always have constant type of extrusion throughout your bioprint. Okay. So did I help to answer the question?
Yes, sir. Yes, sir. It's helped a lot to me. And is there any silicone printers in our country?
Uh, I did hear of a company based in ISC Bangalore, but I think they are not selling their bioprinter. They are making various, they're using silicon to make various silicon based structures. I think they use it also for making breast implants. But I don't know, I've not heard about them in the last 2 or 3 years. So I'm not sure about them. Apart from that, there are some companies in Europe also who are making printers specific to silicon and rubber type of material. Now, silicon has both bioprinting as well as industrial applications. So these companies are trying to target both types of applications. Their extruders are much more customized to work with silicon. And definitely, I mean, if you use a normal pneumatic extruder, you may initially face some problems, but if you can make certain suitable modifications, you can improve the printability of silicon using that. And of course, by also having the right silicon mix, that also is very important when you want to print with silicon.
Okay, sir. Thank you very much. And is there any provision to mix silicone with calcium silicate materials to prepare a final product for biomedical application?
Yeah, that's a very interesting question now, because this because I have heard of a number of researchers who are trying to mix silicon with various biomaterials. Like in your case, you mentioned about the calcium based product. The when you do that, you will have to carefully prepare the recipe and ensure that either it is completely homogeneous so that you can use a pure pneumatic based extruder, and if you find that it is not pneumatic, it is not homogeneous but heterogeneous or colloidal, then you must use some form of a hybrid extrusion to ensure that you have uniform extrusion throughout. But yes, this is a very interesting area and I encourage you to explore more.
Sure, sir. Thank you. And participants, if you have any doubts, you please take the advantage of the comment box. There is one question, sir.
Yes, please go ahead.
Dear Professor, indigenous extruders such as TCP and MGO. Just a minute, sir.
Yeah, go ahead.
Jayvelu, sir, please unmute your mic and raise your question.
You can type it in the chat window also if you like.
Yes, sir. He already expressed his doubt. Dear Professor, indigenous extruders such as TCP and MGO.
Magnesium oxide. Okay.
Magnesium oxide.
Okay, but what's the question about?
That's what.
Maybe you wanted to know if there are some extruders that can work with TCP and magnesium oxide. Mixing both of them. Okay. Yeah, yeah, it can work. So TCP magnesium oxide. So there have been few papers working with magnesium oxide. and I've seen some of them. And of course, TCP is a very popular material to work with. I have not heard of mixing both of them together, but certainly you can try to do that. That is a good area of research. In order to work with that, you'll have to first prepare the recipe for TCP magnesium oxide, mix them together, use a suitable solvent, create a paste, and then depending on the characteristics of that paste, you must choose the extruder. I am not an authority on this, but I would suspect that your paste will be a colloidal, or at best, I mean, it is very difficult to create a homogeneous mixture of TCP and magnesium oxide because, okay, so which 3D printing techniques give more surface roughness and hardness? Okay, I mean, if you want to create surface roughness and hardness, it is actually more a characteristic of the ink per se. Both pneumatic and syringe pump and even inkjet or hybrid extruders, they will give you similar type of surface roughness. But your ink, if it is more porous or if it allows you, I mean, after the extrusion, if it tends to expand a little bit or become coarse, that will determine the surface roughness and hardness. Okay, and yeah, so I think the ink is far more important here, and when you work with both magnesium oxide and TCP, I think you will have to work more on creating the ink which has both magnesium oxide and TCP in it. And so if you find that your mix is colloidal in nature or heterogeneous, I would suggest that you use a hybrid type of extrusion, or at least a syringe pump based extrusion, so that you get uniform extrusion, so that your bioprint is uniform. If you use pneumatic, you have the advantage of being able to extrude with a lot of pressure, but the problem is you may not get uniform extrusion. The volume extruded may not be the same everywhere. So that may be a structural issue for you. Did I answer the question?
Yes, sir. Yes, sir. Yes, sir. Thank you, sir. Thank you, sir.
Most welcome, sir.
Thank you very much, sir. Yes, sir.
Most welcome. Okay, I think this surface roughness is from another person. Sorry, I kind of missed that. So she has put in another chat window. She wants to do FDM. Okay, so if you want to use FDM, you will have to work with filaments. So you can either use the commercial filaments that are somewhat limited, because there's not a lot of filaments that are commercially available. Mostly the popular ones, ABS, PLA, HIPS, nylon, PETG, and so on. If you want to make customized type of filament, you do have filament fabricators with which you can make these customized filaments, but it's a little difficult to ensure uniform thickness of the filament. And if you want to create surface roughness and hardness, I think in a FDM you will get. I mean, if you use a higher layer thickness, you will get more roughness. The other ways to create a roughness would be to add suitable solvent, which can kind of, so after your 3D print is done, if you add some solvent, it can make the surface more rough, or in some cases it makes it smooth. In some cases it can make it more rough as well. Say for example, in glass, when they want to make frosted glass, okay, so they use a boric acid on a completely smooth glass surface, and what that does is the acid will eat away selected portions and make it very rough, and that's how you get frosted glass. So similarly, in your FDM, when you want to experiment, you may use this method of adding solvent to introduce roughness or hardness. And of course, when you are 3D printing, don't use ironing, because ironing will make it very smooth. Use maybe a higher layer thickness, higher layer height, maybe 3.3 mm or so, and that can create more roughness. Did I answer your question?
Sir, for bone implants, FDM is suitable, sir? We have to print the
See, the problem with FDM is, as I said, you have only a very limited array of filaments. Okay, so the
Yes, sir.
only filament that is available would be maybe PCL filament. Okay, but even PCL is not very suited for implants per se. I mean, normally
Yes.
we want to work with either TCP or some calcium, or as you mentioned, as the earlier question, the person was saying that you want to do with magnesium oxide. So magnesium,
Okay, sir.
calcium, those are the more commonly used materials for bone or cartilage. So you may find it difficult to get filaments of that type of material.
We are planning for biocompatible, biodegradable materials for bone implants. So
Okay.
that FDM is suitable or not, we
Yeah,
have to
I think
clarify that.
FDM will not be very suitable because you will not get the because in FDM you require filament, right? So
Yes, sir.
you
So which one is more suitable, sir? SLM or SLS, or which one?
I think a bioprinter will be more useful for you, because then you can use either, I mean, whichever type of material you want to use, like TCP or calcium or magnesium or hydroxyapatite, or you can then make it into a paste and then use it in a bioprinter to print it.
Oh, okay, sir.
Yeah, if you
Polymers. Mm.
you can reach out to me, like, or go to our website in Alfatek Systems, or send
Oh,
me an email,
okay, sir.
and I can give you more options for you.
Oh, okay, sir. Okay. Thank you, sir.
Most welcome, Devika. So, in case someone may have missed noting down my email or phone number, here it is. You can note it down and reach out to me. You can also go to our website, alphatechsystems.com, and there you can see more details about our printers. I'm sorry, I've not updated it too much, but at least the basic you will get. And you can also, so I think if you send an email, it is always better, because then I know exactly what is your application, and I can then recommend the most appropriate bioprinter, because nowadays there's such a huge number of printers that are available. So which one to use for which application, that is also something that you need to consider. Okay. Any other questions?
Dear participants, any other questions would like to ask to Sumant sir?
Sir, can we blend polymers with this hydroxyapatite TCP material, sir? Like polymers,
Yes.
like
Yeah. So here I will. So this is work that has already happened at Sri Chitra, SCT-MST Trivandrum, and for this, what they do is they have worked with various polymer pellets and combined it with TCP. So specifically, they have combined PCL pellets with various TCP and ceramic type of materials, powders, and then extruded it. So for this, they used something called a pellet extruder 3D printer. Okay, so there is of course the bioprinter, but you can a pellet based extruder or 3D printer will be much more appropriate here. So in a pellet based extruder 3D printer, what you do is you fill the hopper. So the pellet extruder 3D printer contains a hopper in which you can fill it up with various polymer pellets or powders. Okay, and then it has a lead screw. So the lead screw draws in the pellets and melts the chamber, mixes it together, and then extrudes it and makes the 3D print. Okay, so the actual the extruder is normally very big. It weighs about almost 2-3 kgs, and it is mounted on a 3D printer. Okay, so we sell this kind of a pellet extruder 3D printer also. It costs about 6 to 7 lakhs, And using this type of pellet extruder, I think it will be much more useful for you, because then you can mix various polymer pellets, PVA, PCL, PLA, mix it with various powders, whichever you want to do, various ceramic or other type of biomaterials also, and print it out into whatever shape or size that you want to make.
Sir, how can we use that facility, sir? Like we are only students actually.
If you like, you can reach out to me. We have this pellet extruder in our facility, so we do provide access to this facility on a payment basis. So if you want to, if you send out the materials to me, like whatever type of material you have, and if you tell us what shape or size you want to do, you need not purchase the printer. You can reach out to us and we will 3D print it, and then we will send it to you.
Okay. Actually, I wanted to characterize the different properties, sir. So, okay, sir, I'll definitely talk to you, sir. I'll contact you.
Yeah, sure. Send me an email, sb@alphatech. You got that, right? So send me an email, and I can help you out.
Okay, sir. Okay, thank you, sir.
Most welcome. Most welcome.
Very much. Thank you very much.
So that's for all the other participants also. In case you feel you are not able to purchase any 3D bioprinter and you need access, you can reach out to us, and then we can talk to you, and we can help you. In some cases, we even provide free samples. So it depends if it's something that is very interesting or very novel, or it is of I find it very interesting. We also have that kind of a mechanism. So not always commercial, but we are also into R&D. So sometimes if it's something that we allocate certain amount of our money to doing this kind of R&D. So if your idea is something that we think is very novel or very interesting, we can use our funds. And if not, you can always on a payment basis, there is no problem. You can always reach out to us, and we can make the samples and send it to you.
Okay, sir. Thank you. Thank you, sir. Thank you very much.
Most welcome.
Any other questions from the participants? Okay, Sumant sir, thank you very much for your presentation, and thank you very much for spending your valuable time to enlighten our participants' knowledge as well as our knowledge. Hello, Sumant sir.
All right. Sorry, I was just saying thank you to all the organizers for inviting me for this session, and also to all the participants with whom we could spend an hour and we could share our knowledge together. And in case any of you would like to like help on any of your projects, or if you'd like to do some work together, please do reach out to me. You have my email and contact details, or you can go to our website alphatechsystems.com and reach out to us. And we wish you all the best in your future endeavors, and keep 3D printing.
Thank you, sir.
Thank you, sir.
Thank you. Thank you. Have a good night to everyone. Okay.
And dear participants, we shared today's feedback link in the chat box. Please complete today's feedback.
Sir, please kindly fill the feedback forms as early as possible. Whatever I have posted now is the second day.
What about yesterday's feedback, sir?
Just I had posted, sir. Yesterday's
Yesterday?
feedback.
Now, today?
Today is already posted, sir.
Today I have filled, sir, but yesterday not posted. No.
No, just now I have posted in the chat box. Please refer to that. I have mentioned clearly day 2 feedback link, day 3 feedback link, like that.
సంతోషంగా 25th వెడ్డింగ్ యానివర్సరీ చేసుకుంటుంటే అది స్పాయిల్ చేయాలని కేక్ లో పాయిజన్ కలపడం ఏంటి?
Thank you all. Thank you for patiently listening to the sessions of the third day of the FDP. Thank you.